In this video, we are going to talk about the pH of polyprotic acids. A polyprotic acid is an acid that contains more than one proton. So, example, if you have H2S, hydrogen sulfide, this is an example of a polyprotic acid. Another example is H2SO4, which is sulfuric acid. And then phosphoric acid is also a clear example of a polyprotic acid. For example, if you take hydrogen sulfide, now first it will dissociate and give us the hydronium ions and then HS minus ion. Then in solution, this HS minus ion will dissociate again to give us the hydronium ions and then S2 minus ion. So this one will be the first acid dissociation constant, Ka1, and then this is the second acid dissociation constant, which is Ka2. So let's take some examples and then explore this concept. Calculate the pH and concentration of each of the species in a 5.0 molar H3PO4 solution. Then we've been given Ka1, Ka2, and then Ka3. So in order to know the species, the first thing is that we must write the system of equations for the dissociation of the phosphoric acid. So let's write the first one. So we know for sure that phosphoric acid is a weak acid. So the first dissociation will be dissociation to hydronium ions and then H2PO4 minus ions. So let's use the ICE table to calculate the concentration of the hydronium ions and H2PO4 minus ions. So the initial concentration of the H3PO4 that we're given is 5.0 molar. But we know that the initial concentration of the hydronium ions and the H2PO4 minus ions are all 0 respectively. Now the change, this one will gain ion, so this one will be plus X. This will also gain ion, so plus X, because their mole ratio is 1:1, and this will lose ion, so the change here will be minus X. The equilibrium concentration 5 minus X molar will be for this, and here will be 0 plus X is X, 0 plus X is also X. So this actually is the first acid dissociation constant, Ka1. So let's write the equilibrium expression for Ka1. Ka1 is equal to concentration of the hydronium ions times the concentration of the H2PO4 minus ion divided by the H3PO4. So we're giving Ka1 to be 7.5 times 10 exponent minus 3. This is equal to X times X, which is X squared, divided by 5 minus X. So let's use the approximation in this case. Then after we'll verify the approximation using the 5% rule. That is to approximate that 5 minus X is approximately equal to 5. So this becomes 7.5 then times 10 exponent minus 3 equals X squared divided by 5. So X is equal to square root of 5 times 7.5 times 10 exponent minus 3. And therefore, if you compute this, you get X equals 0.19 molar. So this implies that the concentration of the hydronium ions, concentration of the H plus ions is equal to 0.19 molar. And then the concentration of the H2PO4 minus ions is also equal to 0.19 molar. The next thing we are supposed to do is that you see that this H2PO4 minus will also dissociate again. So let's write the equation for the dissociation of H2PO4. So H2PO4 minus ions will dissociate in solution to give us the hydronium ions plus HPO4 2 minus ions. So what is the initial concentration of the H2PO4 minus? That's what we found here, 0.19. And then for the H plus, it's also 0.19. Actually, it's molar, so let's bring the molar. But this is 0 for the initial concentration. Then the change here will be minus x, here is plus x, and here is also plus x. And the equilibrium concentration here will be 0.19 minus x, here is 0.19 plus x, and here is x. So let's write the expression for Ka2. We know that Ka2, because this is the second dissociation, so it will be characterized by the second acid dissociation constant, which is equal to concentration of the H plus ions times concentration of HPO4 2 minus ions divided by the concentration of the H2PO4 minus ions. So we have already established that Ka2 equals concentration of H plus times concentration of HPO4 2 minus divided by concentration of H2PO4 minus. From the question, we were given as 6.2 times 10 exponent minus 8, and this is equal to 0.19 plus x, that is concentration of the H plus, times x divided by 0.19 minus x. Now, because this acid dissociation constant is very low, then we are going to make the approximation that 0.19 plus x equals 0.19, and 0.19 minus x equals 0.19. So we'll get 6.2 times 10 exponent minus 8 equals 0.19x divided by 0.19. So these two will cancel out. So we find out that x is equal to 6.2 times 10 exponent minus 8. In other words, the concentration of the HPO4 2 minus is equal to 6.2 times 10 exponent minus 8 molar. Now let's write the equation for the third dissociation. So we know that the HPO4 2 minus will further dissociate into solution to give us H plus and then PO4 2 minus and ions in solution. So the initial concentration of HPO4 2 minus is 6.2 times 10 exponent minus 8 molar. Now, the H plus concentration is going to be the original that will go from Ka1 plus the one we got from Ka2. And the one we got from Ka1 was 0.19. And then the one we got from Ka2 is this. And you see that this is far less than 0.19. So if we add it, we still get 0.19. So here is 0.19 molar. And then this is 0. The change here is minus x plus x and plus x. Then the equilibrium concentration here will be 6.2 times 10 exponent minus 8 minus x. There's 0.19 plus x, and then here's also x. So let's write the expression for Ka3. Ka3 is equal to concentration of the H plus ions, then times concentration of the PO4. Sorry, this PO4 is 3 minus. I'm sorry about that. 3 minus ions, then divided by concentration of HPO4 2 minus ions. And then from the question, we're given K3 as 4.8 times 10 exponent minus 13, and that is equal to 0.19 plus x times x divided by 6.2 times 10 exponent minus 8 minus x. So you see in this case too, this K3 is also very small, and therefore we'll make the approximation. So 4.8 times 10 exponent minus 13 equals 0.19 x divided by 6.2 times 10 exponent minus 8. So x is equal to 4.8 times 10 exponent minus 13 and times 6.2 times 10 exponent minus 8 divided by 0.19. And if you do this, you get x equals 1.6 times 10 exponent minus 19 molar. So So it implies that the concentration of the PO4 3 minus is equal to 1.6 times 10 exponent minus 19 molar. Now, the question also asks us to find pH. And we know that pH is equal to minus log of the concentration of the H plus ions. And if you see, the total H plus ions will be equal to the H plus ions we got in the case of the Ka1, which was 0.19, plus in the case of Ka2, which is 6.2 times 10 exponent minus 8. Then in the case of Ka3, which is plus 1.6 times 10 exponent minus 19. But if you add all of this is approximately 0.19 molar. So the pH will be equal to minus log of 0.19. And if you do this, you are going to get 0.72. So let's list all the ions that we got. So we got the pH to be equal to 0.72. Concentration of the H plus ions equals 0.19 molar. Then concentration of the HPO4 minus ions, we got that as equal to 6.2 times 10 exponent minus 8 molar. And then concentration of PO4 3 minus ions, we got that as 1.6 times 10 exponent minus 19 molar. So these are the various concentrations of the various species that we're supposed to calculate. Now you can see that the concentration of the HPO4 minus is equal to Ka2, and that is very important information that we will later talk about. Calculate the pH and the concentration of all the species present in 0.02 molar of carbonic acid. So now let's write the dissociation of carbonic acid. H2CO3 is a weak acid. To dissociate into H plus ions plus HCO3 minus ions. So this is the case of Ka1. So the initial concentration, when it comes to H2CO3, we're given 0.02 molar. And then H plus is X, and here is also, here is 0, and this is also 0. The change here is minus X, plus X, and here is also plus X. And then the equilibrium concentration, here is 0.02 minus X. Here is X, and here is X. So let's write the expression for Ka1. Ka1 is equal to concentration of the H plus ions times the concentration of the hydrogen carbonate ion divided by the concentration of the H2CO3. So Ka1. Now, the first acid dissociation constant for carbonic acid is 4.3 times 10 exponent minus 7. So 4.3 times 10 exponent minus 7. This is equal to x squared divided by 0.02 minus x. So if you look at this is very small. So let's do the approximation. We'll test it with the 5% rule. X squared is equal to 4.3 times 10 exponent minus 7 and times 0.02. So x is equal to square root of 4.3 times 10 exponent minus 7 times 0.02. And if you do all of this, you are going to get 9.3 times 10 exponent minus 5 molar. So this implies that the concentration of H plus ions, So this implies that the concentration of the H plus ions is equal to 9.3 times 10 exponent minus 5 molar. And then the concentration of HCO3 minus ions is also equal to 9.3 times 10 exponent minus 5 molar. Now let's use the 5% rule to check whether our answer is correct. So 5% rule. So you see that here is 9.3 times 10 exponent minus 5 divided by the original concentration, which is 0.02 times 100%. And this is equal to 0.04%, which is far less than 5%. So our approximation is right. Now, the question we did previously, we're supposed to check with the 5% rule. So let me just quickly do it here and we'll continue. We got concentration of the H plus ions as 0.19, and that was divided by the original concentration, which was 5.0 molar, then times 100%. If you do this, it's equal to 3.8%, and that is also far less than the 5% rule, and that's how come our approximation was right. So now let's write the second acid dissociation for carbonic acid. So the HCO3 minus ion will dissociate again in solution to give us H plus ions plus CO3 2 minus ions. So the initial concentration for this, remember we already got that as 9.3 times 10 exponent minus 5 molar. And this is also 9.3 times 10 exponent minus 5 molar. And here is 0. Now the change here is minus x, here is plus x, and here is also plus x. So the equilibrium concentration here is 9.3 times 10 exponent minus 5 minus x. Here is 9.3 times 10 exponent minus 5 plus x, and here is plus x. So let's write the expression for Ka2. Ka2 is equal to concentration of the H plus ions times the concentration of the CO3 2 minus ions divided by HCO3 minus ions. Ka2 for carbonic acid is 5.6 times 10 exponent minus 11. That is equal to x times 9.3 times 10 exponent minus 5, then plus x divided by 9.3 times 10 exponent minus 5 minus x. I see that this is so small, so let's make the approximation. Then what will happen is that 5.6 times 10 exponent minus 11 is equal to, if you approximate this is 9.3 times 10 exponent minus 5x. And then here too is the same thing, divided by 9.3 times 10 exponent minus 5. So this one and this one will cancel. So we'll get x equals 5.6 times 10 exponent minus 11 molar. So what it means is that the concentration of the CO3 2 minus ions is equal to 5.6 times 10 exponent minus 11 molar. Now let's find pH. We know that pH is equal to minus log of the concentration of the H plus ions. But the H plus ions, we got the first one. That one was a value of 9.3 times 10 exponent minus 5. You can see that this one is 5.6 times 10 exponent minus 11. If you add the H plus from the first dissociation plus the second dissociation, everything will be approximately the first dissociation, which is 9.3 times 10 exponent minus 5. So pH therefore is equal to minus log of 9.3 times 10 exponent minus 5. And if you do this, you get 4.03. Calculate the pH and the concentration of all species present in 0.1 molar H2SO4. Now, let's first write the acid dissociation of H2SO4. Contrary to all the examples we've done in the first instance, now H2SO4 is a strong acid, so the first dissociation will be only a forward reaction. There will be no backward reaction in this case. So everything will dissociate into the H plus ions and then the HSO4 minus ions. Now, this one was 0.1 molar. That's the initial concentration. So here will be 0 and 0. So the final concentration here will be 0, and then here will be 0.1 molar, and this will also be 0.1 molar. So what will happen is that the HSO4 minus ion will undergo a reversible reaction, because remember this is a weak acid, so the dissociate into the H plus ions and then the SO4 2 minus ions. Now, the initial concentration of the HSO4 minus ions is 0.1 molar. But then we also know the initial concentration of the H plus ions to be 0.1 molar. But we don't know for the SO4 2 minus ions is 0. Now the change here is minus X, here is plus X, and here is also plus X. So the equilibrium concentration here will be 0.1 minus X. Here will be X, and here will also be X. So let's write the acid dissociation constant, Ka, for this. So you see that Ka will be equal to concentration of H plus times the concentration of the SO4 2 minus ion divided by concentration of the H2SO4. The Ka for sulfuric acid in this case is 1.2 times 10 exponent minus 2, and that is equal to here is 0.1 plus X. Please, let's make this correction because there's 0.1 here. So here is 0.1 plus X. So this is X times 0.1 plus X, then divided by 0.1 minus X. So let's use the approximation, and after we verify with the X, with the 5% rule. So if we do the approximation, 1.2 times 10 exponent minus 2 is equal to 0.1x divided by 0.1. So this and this will cancel. Find out that x is equal to 1.2 times 10 exponent minus 2 molar. Now let's check with the 5% rule. So this is 1.2 times 10 exponent minus 2 divided by the original concentration, which is 0.1 times 100%. And then if we do this, we are going to get 12%. Now 12% is far greater than the 5%, and therefore this our approximation cannot stand. For that reason, we need to go through the long method to find the value of x. So if we cross multiply, we find out that x times 0.1 plus x is equal to 1.2 times 10 exponent minus 2 and times 0.1 minus x. X times 0.1 is 0.1x. The x times x is x squared. This is equal to, now 1.2 times 10 exponent minus 2 times 0.1 will be 1.2 times 10 exponent minus 3. And here will be minus 1.2 times 10 exponent minus 2x. Now, if we rearrange and we do the subtraction, you see that here is x, and then here is also x. So we will get x squared, then plus 0.1x. Then here becomes plus 1.2 times 10 exponent minus 2x. Then minus 1.2 times 10 exponent minus 3. And that is equal to 0. So we'll come and get x squared. Now writing everything in decimal, then plus 0.112x and minus 0.0012 equals 0. Now you see that this is equation of the form ax squared then plus bx and plus c equals 0. So we can use the quadratic formula. X is equal to minus b plus or minus square root of b squared minus 4ac divided by 2a. So in this case, you see that the b is 0.112. So we are going to get minus 0.112 plus or minus square root of 0.112 squared minus 4 times a is 1, then times the c. The c is minus 1.2 times 10 exponent minus 3. All of this divided by 2a, 2 times 1. So that is x equals. So x is equal to If you do this, you get 0.056 plus or minus 0.066. Now, we cannot have negative concentration, and therefore, we are only going to get x equals, sorry, there's a minus here. So, minus 0.056 and plus 0.066, and x will be equal to 0.01 molar. So what this means is that the concentration of the SO4 2 minus is equal to 0.01 molar. Now, the concentration of the other species is the H plus ions, and that will be equal to the original concentration that we had, which was 0.1 molar, plus this concentration coming from the dissociation of the HSO4 minus, which is plus 0.01 molar. So this is equal to 0.11 molar. So now we can find the pH. So pH is equal to minus log of the concentration of the H plus ions. That's equal to minus log of 0.11. And if you do this, you get pH equals 0.96. Finally, let's calculate the concentration of the HSO4 minus ions. So remember that from the dissociation, we got the original concentration as 0.1 molar. But this further dissociated to give us a concentration of H plus of 0.01 molar. So the amount of HSO4 minus ions that is truly in solution is going to be 0.1 molar minus 0.01 molar, and that will give us 0.09 molar. So the concentration of the HSO4 minus ions in solution, 0.09 molar.